Alrighty, so let's go ahead and jump into this, taking it nice and slow. So this is chapter 6, and in this chapter the goal here is to learn, as it says, about magnetism and electrostatics, static electric charges, electric charge in one spot, let's say. And this is all due to a phenomenon called electromagnetism. Okay, so originally, when discovering all these truths about physics, we discovered electricity, we discovered magnetism, right, separately. Okay, and it was only through the work of some important physicists in the 1800s that we developed a understanding that electricity and magnetism were two sides of one coin. That coin is called electromagnetism. Okay, so electricity and magnetism are both phenomena from one thing called electromagnetism. If you went through physics with me, we've talked about electromagnetism and electromagnetic waves and stuff like that. But let me give you just a couple of important things to start with here. So you know about magnets, right? You all probably have magnets on your refrigerator, and you know about electricity, right? Electricity lights your homes and powers your phones and stuff like that, right? But you may, before reading this, before going through this, you may not know that they both are manifestations of the same thing, right? Electromagnetism. So let's take a look. First off, Hans Christian Ørsted in 1819. Okay, so there's important names in the history of physics, and his is one of them. There's even a law called Ørsted's law. So this is 1819, Danish physicist, and his important discovery was that nearby electric currents will deflect magnets. Okay, yeah.
And so I was having a hard time just understanding that little piece as soon as I started reading it, because like this book, some of the words really do mean some of the opposite of what they are.
Sure.
Deflect to me is like pushes away,
Yeah.
pushes it somewhere else. But in this, it actually means that it's like pulling it towards it.
Well, let me phrase it like this. A nearby electric current will exert a force on a magnet. Okay, that force can be repulsive or attractive, depending on which pole of the magnet is facing the electric current and which direction the current is moving, right? But so just think about it as the electric current exerts a force on the magnet. Magnets react to magnetic fields. So his discovery was that moving electric currents generate a magnetic field, which then can act on a magnet. Okay, so you can create magnets by running electricity through wires. That's really the discovery here. So ignore direction right now and just understand that there is when electricity moves, when electric current moves, and in the subsequent chapter we'll learn at what electricity is, but when electric current moves, a force is exerted, and that force can be called the magnetic force. Okay, so exerted, yeah, a force is acting upon the magnet, the nearby magnet. So all moving electric charges, again, we haven't given a definition of what an electric charge is. This is the first slide that we're going through. But all moving electric charges generate magnetic fields. This is huge because what it turns out to mean is that, and not at face value it doesn't mean this, but what we science discovered that it means is that we can create motors and generators. We can generate electricity by creating, or by simply moving electric fields around. Okay, we can create more electricity by moving electricity, or we can create electricity by moving magnets around, right? Magnets can create electric current. Electric currents can move magnets, okay? So we still have more work to do to understand why, but yeah, so this magnetic field can disturb nearby electric devices. For example, if you're in medical assisting right now, which of you have done EKGs? Have you all done EKGs? A few of us have, okay? What has Linda told you about doing EKGs? What, one more time?
Like not to talk or
Not to talk and move, right? How about any other electric devices?
definitely like cell phone or clock.
Yeah.
No.
And why, right? So the why is the electric cell phone has a magnetic field. Okay, so your little cell phone battery running is a moving electric charge, right? Running electric charge through your phone, and that generates a small magnetic field. Well, Orsted says that magnets can affect electric current, and electric current can affect magnets, okay? All moving electric charges have a magnetic field, okay? So your cell phone has a magnetic field around it. That magnetic field can interfere with the magnetic field running through the EKG electrodes. And it's not that we're not worrying that your EKG electrodes will alter how your cell phone works. We're worried that, which in principle it can, but we're worried that your cell phone's rather magnetic field will affect the EKG's magnetic field running along the magnetic field around the electrode wires, thereby affecting the electric current in the electrode wires, changing the readout that you have on the screen or on the paper or the screen, whatever it is, right? So your phone or your electric watch or any other electric device, pacemaker in the patient, has an electric current. That electric current has a magnetic field. That magnetic field interacts with the magnetic field running through the electrode wires, changing the electric current in the electrode wires. Okay, so they interfere. We just simply call it interference. In fact, you can have interference in your EKG device just by having the lights on in your room. We call it 60 hertz AC interference, 60 hertz AC interference, because the electricity coming through the wires in the walls is a type of electric current called AC, or alternating current, and it jiggles back and forth 60 times per second, 60 hertz. We'll talk more about that later. But the point is that that's just it. Electric currents have magnetic fields, and they interfere with other magnetic fields, messing with the electric currents in those other lines nearby. We'll learn that this is actually a really useful phenomenon because all AC motors, and where do you have electric motors in? Well, you have electric motors in electric cars, right? You have electric motors that roll down your windows and turn your windshield wipers, right? You have electric motors that start your car, right? So your car can't work without, even gas-powered cars cannot operate without electric motors, right? We don't have to roll up our windows down and up anymore because of electric motors, and all of those things are developed or were developed because of that phenomenon of interference. Okay, we're going to learn a lot more about that. Okay, so here's the thing. All matter, which electric current runs through matter, all matter is sorry, I poked you. All matter is built on atoms, okay? Atoms are built on these elementary particles. And so just to briefly remind you, the particles that atoms are made of are called electrons, protons, and neutrons, okay? Now, take the little picture of an atom that you probably have inside your head, right? There's a nucleus, a dense center to an atom. In that dense center are protons and neutrons. The nucleus of atoms have a positive electric charge. So again, the picture should be something like, I've got a positively charged nucleus. Don't worry about what charge means, just note that this is an electric charge. Electric charge is built in. Okay, so electricity, electric charge, is built into the elementary particles of our universe. Okay, we figured out how to take advantage of the electric charge in order to generate electricity, electric current, but electric charge is just built in. Don't ask me what electric charge is, it's built into the universe, okay? And there are positive electric charges, and then there are negative electric charges. Nuclei of atoms are all positively charged. And then you probably understand at least that electrons of atoms orbit around the nucleus, okay? An atom is happy and stable when there is an equal number of positive charges in its nucleus and negative charges in orbit around it, okay? I've drawn a super duper simple atom here. I drew hydrogen. Hydrogen only has one nucleon and one electron, okay? But atoms are built on electrons, protons, and neutrons. Now here's the thing. All of these fundamental or elementary particles, those are both interchangeable terms, fundamental particle or elementary particle, they all have three properties, okay? So they move, so we're ignoring the fact that they move around right now, okay? But if you just took, and you're not going to do this, but if you took a proton and just held it, right, or took an electron and just held it, you'd say, what are its properties, okay? Well, they're made of matter, okay? So matter has mass. All elementary particles have mass, okay? And a electron has a mass, a proton has a mass, a neutron has a mass, okay? They all have mass. That means if you put them on a scale, which again you're not going to do, but follow me through the thought experiment. If you put them on a scale, they would weigh something, okay? They have mass, okay? Which is why you, being built out of protons, neutrons, and electrons, weigh something here in Earth's gravity, right? You have mass, okay? You're built from these things, and so these things have mass, so you have mass, okay? Your mass didn't come from nowhere, okay? You're built out of smaller pieces, and these pieces all have weight or oomph to them, okay? Protons are much, much heavier than electrons. The relationship between protons are about 2,000 times heavier than an electron. 2,000 times more massive. Okay. Remember the first slide we did. Moving electric charges generate magnetic fields. Okay? So, any moving electrically charged particle will create a magnetic field. So hang on to that. We're going to keep going. So all fundamental or elementary particles have mass. Electrons have mass, protons have mass, neutrons have mass. Good. That's one thing. All elementary particles have charge. You've hopefully figured that out because we just said protons have a positive electric charge and electrons have a negative electric charge. So a proton and an electron are much, much different in mass. A proton is 2,000 times heavier than an electron, but they have an equal amount of electric charge. Opposite, but equal amount. So it's not as if an electron has a negative electric charge, but it's smaller in magnitude than the protons. They have equal and opposite electric charge. So we just say protons have a charge of +1, electrons have a charge of -1. Don't worry about what plus and minus mean. Just pay attention to positive charges are opposite of negative charges. And they attract each other. Positive and negative charges attract. Opposite charges attract. Opposites attract. Like charges repel. Okay, so if you're following at this point, you've learned two things. That all fundamental elementary particles have mass and electric charge. Okay? Yeah.
Jumping ahead.
Please.
So the positive charge is the pull, and the negative charge is the, no, I got that back. The negative charge is being pulled, the positive charge is pushing.
Sort of. Let me give it to you, and I'm almost not going to want to. I'm almost not going to want to give you more than that. That's why I said don't worry about what they mean.
Okay.
I was you as a student. I'm like, what do you mean positive? What do you mean negative? And my instructor's just like, don't worry about that. Just know that they're opposite.
Yeah,
that's all you need to know. But let me give you a tiny bit more than that. Okay. So take a proton. It has an electric field around it. I told you the electric field is just built in, right? That electric field points away from the proton. Okay? Okay, so it exerts its force outward. Okay? The negative electron, its electric field points toward it. The opposite. That's the only difference, is direction that the charge is oriented. Okay? Because of this, positive and negative charges attract, and negative and negative charges repel, and positive also repel each other. Okay, That's the maximum I want to give you. If you want to know that, then you got to go learn Maxwell's theory of electromagnetism and the field equations and all this god awful stuff that you don't want to learn. By the way, I can give you all the information you want on that, but it's not in the curriculum for the school. Okay, all right. Okay, so you've learned so far. Every elementary particle has mass and electric charge. Okay, and if you remember from the first slide that all electric charges, when they move, generate magnetic fields. Okay, there's movement left and right, up and down, forward and backwards. You can like move in 3 dimensions, right? Okay, so anytime an electrically charged particle moves in one of those 3 dimensions, a magnetic field is generated. Okay, there's a third type of movement. So an electron, in principle, you can hold it still. It's just here. You can put it here. Again, in principle, not practice, but in principle, you can put it here, hold it, hang on to it, and it can sit still in space. Okay, but there's a fundamental property for all these elementary particles that you cannot get rid of. Okay, all elementary particles have built in an inherent amount of something called spin. Okay, spin's not hard to understand. You've seen the Globetrotters take and spin a basketball on their hand, right? On their fingertips, right? Or somebody who is better than me can do that, right? But the point, I cannot do it. I've tried. But the point is that you know what spinning things look like, right? Okay, so you're gonna hear things like, what they even say it here. Spin is an exotic type of motion that electrons, protons, and neutrons all share. Well, why is it exotic? If normal things in the everyday world spin and we go, yeah, that thing's spinning, why is it exotic when an electron or proton does it, right? Well, what are you picturing in your head when I draw a picture of an electron or proton? What does it look like to you? A ball, right? Okay. Like that, right? Okay. Here's why it's wrong to think about it like that, okay? These objects are not a ball, okay? In fact, they're not even, they don't have a spatial extent as a sphere, okay? They are what are called point particles, okay? So a single point cannot rotate, okay? However, they do. So a single point in space can't spin like a ball, okay? But electrons and protons have spin. They spin in a very real way. Just it's not exactly like a basketball spinning, okay? We call it spin. More correctly, it is called angular momentum, okay? Momentum is just mass times velocity, but don't worry about that. Angular momentum is an intrinsic amount of rotation, okay? The Earth has angular momentum. You have angular momentum if you spin around in a circle, okay? An ice skater, figure skating, you guys ever seen figure skating? I love watching figure skating, by the way, right? What do those figure skaters do sometimes? Sometimes they go into these spins, right? They have their arms out, and then what happens when they pull their arms in as they're spinning? They spin faster. When they pull their arms in, they spin faster, and when they stick their arms back out, they spin slower, right? They can control the rate of their spin, right? That's because angular momentum is what's called a conserved quantity, okay? If that, and this would be terrible for the ice skater, but if that ice skater had no friction with the ice, right, and they went into a spin, they would never stop spinning. They could slow down their spin by increasing their radius, or speed up their spin by smallifying their radius, minimizing their radius, but they would continue to spin. Angular momentum is a conserved quantity, okay? If that ice skater then bumped into another ice skater who was spinning, they would transfer some of their spin to that ice skater, okay? Angular momentum is a conserved quantity in physics, okay? It is a conserved quantity in protons, neutrons, and electrons. These things spin, okay? So, if you're keeping track, they're massive, they're electrically charged, and they are spinning, which is a type of motion, okay? And it's built into them. They can't get rid of it. You can't take an electron and slow it down so it stops spinning, okay? It has this spin built into it, okay? So, because they spin, you can define an axis on which they're spinning, right? A basketball spins, and you can define the axis that it's spinning on as the south pole being the finger that it's spinning on, and the north pole just being a straight line up from that, right? There's an axis around which the basketball spins. the Earth generates a magnetic field, right? And there's an axis around which the Earth is spinning, right? Because of that reason, we have a North Pole and a South Pole, okay? Um, if you stand exactly on the North Pole, right, you're standing at the axis. Everything is spinning around you, basically, right? You are standing right at the axis of spin. So so it's okay to picture them like a ball, okay, even though they're not actually a ball, okay? Yeah.
At the opposite poles on the Earth, is there like documentation of like things or weird things that could happen to electric devices or any like fun
I don't
facts like that?
I don't know. I haven't checked for documented events, but I have to assume there can be because the magnetic field lines all converge on the North Poles, and you get phenomenon like the aurora borealis in the north and the aurora australis in the in the southern hemisphere, right? Those light shows that you get right up in north and down south, right? What those light shows are from the magnetic fields. The lines all converge and point down towards Earth, right? So they capture particles coming from the sun, and those particles ride on the magnetic field lines, right? Like iron filings would ride on a magnetic field, and you guys ever seen that toy that you put the hair on him, right? The little magnetic toy. No. You know what I'm talking about. Okay. Anyways, so the particles from the sun ride on that magnetic field and all get funneled into one spot at the North Pole and South Pole. And what they'll do is those particles are accelerated by our magnetic field and they run into Earth's atmosphere and they bang into each other and they emit light from that, and that's what those ribbons of light are. So there's already phenomenon that happens. So I have to assume that it can cause electrical phenomena.
Well, I mean, when I asked if there's something that happens because of the electric fields running there, you said the lights.
Yeah. And so one thing to learn is that the Earth's magnetic field, although it can deflect a compass and we can detect it, right, it's extremely weak. It's like magnitudes weaker than your refrigerator magnets are. Okay, so it's there, right? It's detectable in there, but it's really extremely weak. But yes, it does cause phenomena. Okay. All right, so you guys are following this? Protons and electrons have electric charge, and because they have this property called spin, they're spinning, they develop a magnetic north and south pole. Okay, they develop a magnetic field. They all have a built-in magnetic field because of their built-in electric field. The orientation of the magnetic field for an electron or proton. And so we describe them as either being spin up or spin down. In a moment here, I'll give you that, and I'll give you more on that. But for example, protons with clockwise spin have their north pole pointed up, and those with counterclockwise spin have their north pole pointed down. Example: in an atom, atoms like to group electrons into pairs of two into what are called suborbitals. These are a spot in the atom where the electrons live, okay? Atoms don't look like that, okay? We show them like that, but they don't look like that. Again, it's not a ball rotating around another ball like the Earth rotates around the sun, okay? But we draw it like that. So it's okay to picture it like that, but it's just not in reality like that, okay? Electrons live in pairs of two, okay, in a spot in an atom called a suborbital. You don't need to know any more than that, so don't stress on that, okay? But when electrons group up into these pairs of two, what they'll do is one electron will be spinning one direction, right? The other electron will be spinning, how do we get this right? The other electron will be spinning, I have to do it with the same hand. The other electron will be spinning the exact opposite direction, okay? So you can think of the direction your hand, if you take one of your hands and let me get this right. It's the right hand rule. Take one of your hands, your right hand, and you notice the direction, put your thumb upward, and you notice the direction your fingers are pointing, okay? That would be the direction of rotation, okay? The North Pole is up when your thumb is up. The North Pole is down when your thumb is down. Look at the direction your fingers are pointing when you do that. When your thumb is up, your fingers point one direction, they rotate one direction. And when your thumb is down, your fingers are pointing, rotating the other direction. This is just a way to represent that one direction of spin and another direction of spin, an opposite direction of spin, would flip the magnetic field from north to south on an elementary particle or on something as big as the Earth, for example. The point is that in an atom, the electrons have to live in pairs of 2 in order for their spins to cancel out. Okay, one spin in one direction, if there's not another electron nearby with an opposite spin, there's an unequal quantity here. Okay, there's more spin in one direction than the other. There's more north pole and nothing to cancel it out. Okay, so what you get in an atom, where you would have in certain circumstances an unequal number of electrons. You have this suborbital full, this suborbital full, this one full, but this suborbital missing an electron would leave a gap here, okay, where the magnetic field can then reach out, and interact with a nearby atom. Okay, if this atom had all of its orbitals full, it would not want to, it wouldn't need to interact with any nearby atoms. For all intents and purposes, it would be inert. It wouldn't interact, it'd be like a noble gas, okay? When an atom is like that, we say the entire atom has an overall magnetic charge, okay? So if you look at this, and this is just 2 dimensions, top and bottom, left and right. So no 3 dimensions here, but that's okay. We're looking at a 2-dimensional thing on a 2-dimensional page. But look at, if you count this, right, in the upper half, so split the atom into like a top and bottom. Okay, so in the upper half of the atom, you have a north pole, a south pole, and a north pole. So you have more north pole at the top of the atom than you have south pole. Okay, but down at the bottom of the atom, you have it equaled out. Everything's equal. At the top, you have a north pole. The north pole is dominant. The electrons that are spin up dominate up at the top of the atom, and at the bottom everything's neutral. So the atom develops a very weak north pole direction and a south pole direction. Said in the terms they want us to have, the atom develops what's called a magnetic dipole. Okay, and this is the simplest type of magnet. It's just a single atom with a north and south pole. Okay. So most atoms that are not inert, that are not in the category of noble gases, will have an imbalance in the number of electrons in these suborbitals, and so most atoms are magnetic dipoles. Dipole just means that there's one pole at the top, another pole at the bottom, north and south pole. Yeah. No.
So in this particular case, so the top's the one that's dominating because there's more pull for the north.
Yeah.
Up top. Can it be flipped by saying that an atom from the south can be missing it and
Sure.
get a south the south pole to be the one that's dominant, so it's just like the opposite.
It would be the opposite, but it would still be the same thing.
Okay.
You're right, but it would still develop a north and south pole.
But would it still be the same charge?
Yeah, it would still have the weak magnetic field, the weak electric charge, weak magnetic field developing a north and south pole. So even if you flip-flop things and took electrons out of other spots, and filled that one that's empty, you would still have a dipole. Yeah. So so all magnetic materials are going to be built out of atoms that are magnetic dipoles. Okay, and if an atom is inert and happy, it's not a magnetic dipole. Those that are like this are magnetic dipoles. The thing that we're going to try to drive home here is that there are only magnetic dipoles. If you take a magnet, something that is magnetized and does have a defined north and south pole, right, and you chop it in half, you're going to have 2 magnets now. One magnet with 2 smaller magnets, each with a north and a south pole. And you do it again, you're going to have 4 magnets with a north and a south pole. Okay, you do it again, you're going to have 8 magnets with a north and a south pole. Every time you do it, you just end up with more magnets, all of them having a north and a south pole. Okay, so the lesson that we're trying to get across is that the magnet is not broken into a north pole and a south pole when you break a magnet in half, right? A magnet all the way down to the individual atoms it's made of, all have a north and south pole. So if you could keep chopping up a magnet, you would just end up with more and more and more small magnets until you had all of the atoms laid out, right? And you'd have that many small magnets. Atoms are small magnets.
So the strength of the magnet comes from the accumulation or the mass of all of those small pieces.
Yes, and in a moment here, we're going to look at the way that they're aligned.
Okay.
Because materials can be, in principle, magnetizable, permeable to magnetic fields, but they might not retain that magnetic field. Okay, that's something we're going to look at, yeah. So yeah, entire magnets with net magnetic fields are called magnetic dipoles. And in something like an iron bar, if you've never like magnetized something, know that like you can magnetize materials. Okay, for example, iron. Regular iron bars or bars of iron that have been magnetized. Iron's a great material for magnetizing. That have been magnetized can lose their magnetic fields. Okay, and so, but if you had an iron bar in front of you and it was not already magnetized, okay, it would have many small regions in it where you'd have groups of atoms that all lined up with each other, and all their magnetic north and south poles all pointed the same direction in some small area. Okay, in another small area, the groups of atoms would all group up with each other and point in one direction in that area, but it would be a different direction in each of these areas. Okay, and in a non-magnetized material. Okay, we would call each of these areas magnetic domains. Okay, so take an iron bar. In it somewhere, there are groups of atoms that are all lined up in one direction. North poles all pointing this way, south poles all pointing that way in that area, and in another nearby area, they're pointing a different direction. That's what's represented down here. Each area where everything is lined up in that region is just called a magnetic domain. Okay? To magnetize this bar, you need to get all of the magnetic fields for all of the atoms all pointing the same direction. Okay? If one domain's pointing that way and another domain's pointing perpendicular to that, then you don't have an organized magnetic field. Okay? If they were pointing, north poles pointing towards each other, let's say there were two magnetic domains nearby and they were pointing towards each other, that would completely cancel out the magnetic field. Okay, assuming the domains were of equal size. So magnetizing things requires you to orient all the magnetic dipoles, all the atoms that are magnetized in one direction.
Like when you rub a magnet on a screwdriver?
Yeah, exactly like when you rub a magnet on a screwdriver. Notice you don't just hold the magnet near the screwdriver, right? You take it and you run it along the length of the screwdriver, right? And several times, right? And you've done this, yeah? Assuming you've done this.
Yeah.
Have you ever dropped the screwdriver afterward?
No, but I noticed that it stops working.
After a little while, right? So some materials have low retentivity. They don't retain the magnetic field, even though you can apply it very easily. That's because the screwdriver has big amounts like iron in it, for example. So yeah, like, your screwdriver that you want to magnetize, if you've ever done this, you can take most screwdrivers, right? It's useful for a screwdriver to be magnetized because you want to put a screw on the end of it, and sometimes you got to get into like tight spaces where you can't like hold your hand to hold the screw. So you want to have a magnetized screwdriver. Some you can just buy that are already magnetized, okay? But if you want to do this at home, you can take a magnet and you can run it along the length of the screwdriver several times, and what that'll do is, before the screwdriver is magnetized, it's like this iron bar with all the magnetic domains pointed in all random directions. All of your atoms are just whatever random direction, okay? You run the magnet along it. Well, the magnet is going to pull all of the magnetic dipoles, all of the magnetized atoms, along one direction. Okay, and so when you orient all of the magnetic dipoles, all of these magnetic domain areas, so that they all line up like that, now you've got a screwdriver with one north pole and one south pole. Okay, let's say the tip of the screwdriver is your north pole, right? You take that to a screw, and it's going to attract that screw. Okay, the screw is a magnetic material that it responds to magnets. Okay, it's a ferrous material, and as long as it's not like an aluminum screw or something like that. So some screws, for example, won't hold on to them. The magnet won't hold on to them, but you can then pick up screws and things like that, which is a useful little tool to have. Problem is that if you leave the screwdriver alone for a long time, it loses its magnetic field. Magnets get weaker over time, okay? You won't necessarily notice this with your refrigerator magnets, but they do get weaker over time, okay? They're just a type of rare earth. So refrigerator magnets are what are called rare earth magnets that just, they have magnetic properties and they hold on to them for a long time. But like a screwdriver that you magnetize, it's not going to hold on to it for that long. And if you drop that screwdriver, right, or run it through another magnetic field, okay, you can ruin that alignment that you just created, okay. Yeah.
I remember in physics in high school we took a nail and then you wrap it super tightly with wire and then you hold it on a battery and it becomes a magnet.
You've created an electromagnet, right? Which has great permeability. You've got a magnetic field that you can create, but just awful retentivity because what happens as soon as you turn you disconnect the wire? Right, the magnetic properties are gone now, right? So what's happening there, right? Well, what's happening is, so in principle, you can do that without the nail, okay? A coil of wire with electricity running through it, remember moving electric charges generate a magnetic field. The only thing that, and we'll look at this in a moment, the only thing that the nail was doing for you, it was helping to orient and concentrate the magnetic field in one direction because it's magnetizable ferrous, let's say, okay? So let's introduce a new term here. Materials that are easily magnetized are called ferromagnetic materials, okay? By the way, that's the same, that electromagnet that you made in high school is the same thing, just on a smaller scale, the same thing that like junkyards do, right? Junkyards that pick up cars with that big magnet and then they can drop those cars, they energize the magnet by it's just a big coil of wire. They energize the magnet by turning on electricity, running electricity through it, magnetized, and then they turn it off, and then it drops the car, right? So it's the same thing happening there, yeah. So materials easily magnetized are called ferromagnetic materials. So yeah, a few different types of magnets that we should be aware of. There are natural magnets called lodestones, which are just ferromagnetic rocks that have weak natural magnetic properties. There are permanent or artificial magnets, conventional magnets made from ferromagnetic materials in various shapes. Typical things are like discs, coin shapes, or horseshoes. And then there are electromagnets. Solenoids are coils of wire with electric current flowing wrapped around an iron bar. Again, the iron bar is the thing that helps to orient the magnetic field. Okay, so 3 types of magnets, and of these 3 types, each of these types are going to have 2 characteristics, okay? So all magnets have 2 characteristics to them. There is one, permeability. Permeability means like, can you get into something, right? Permeable. So in this case, permeability is being used to say the ease with which a material can be penetrated by a magnetic field. So if a material was non-permeable, then it's a non-magnetic material. You know, you can't magnetize plastic, right? A plastic is still made of atoms. The same, not the same atoms, but the same type of thing, right? Atoms that your iron bar is made of. Your iron bar is just made of different atoms, okay? So it's just atoms that everything's made of, and certain atoms do not develop magnetic dipoles and cannot be permeable to magnets. So you can't magnetize certain things. Aluminum, you can't magnetize. Aluminum's a metal that isn't magnetic. So that's the thing. Permeable or non-permeable. Here's the problem. Oh, let me give you the second thing and then I'll tell you the problem. So the second characteristic is retentivity, okay, retention. The ability of a material to hold on to its magnetic field or how long it's able to stay magnetized. So here's the problem. Materials that are able to hold on to their magnetic field or stay magnetized for a long time are low in their permeability typically. Materials that are, so they don't magnetize easily. Materials that do magnetize easily usually have low retentivity, like your screwdriver, right? Easy to magnetize, doesn't hang on to it for very long. To get this right, because what do you want, right? You want a material that's easy to magnetize. Okay, so let's say you're trying to build a magnet, right? You're the best magnet that you can. You want the material to be easy to magnetize, so high permeability, and you want it to hold on to. You don't want to make a magnet and have it not be a magnet tomorrow, right? So you want it to hold on to its magnetic properties, right? So you want high permeability and high retentivity. So what you'll do is, the people who do this, right? Engineers, physicists, chemists, they're going to mix metals together to develop so that we get the ideal properties that we want. So you can alloy certain materials. Alloy means to mix together. You can alloy materials so that you can have all the properties that you want. So we can make all kinds of cool magnets. And you have it. You have some you can have more expensive magnets or cheaper magnets, right? More expensive ones are going to be made of better alloys that are easier to magnetize, stronger magnetic fields, hold on to their magnetic fields for longer. Okay. Let me pause here.